Welcome everyone for this not last, but next to last seminar, SIPTA Seminar of the year. And today we are very happy to receive Beatriz Sinova that Kike will introduce in more details in a few minutes. And she will talk to us about robust statistics and imprecise-valued.
Okay, thank you, Seb. So yes, it is my pleasure to introduce Beatriz Sinova. She's from the Department of Statistics and Operations Research at the University of Oviedo, but she made her PhD thesis between the University of Oviedo and Ghent University. So there was this joint doctorate from Ghent University with Stefan van Alst, and from the University of Oviedo with Ángeles Gil and Gil González. She's been working on the robust statistics with imprecise, with fuzzy data, and in particular with location measures. And at the moment, she's heading or one of the headers of the research group Smire Codire at the University of Oviedo. She's also been a recipient, even if she's super young, she's been a recipient of many awards. An award from the Royal Mathematical Society, the foundation of the bank BBVA, the Best PhD Thesis Award, the award Ramiro Melendreras from the Spanish Statistical Society, also Best Paper Awards at some conference like SMPS conference in 2018. And she's going to talk to us about imprecision, but one of the topics that we hadn't touched in much detail so far here at the seminars, which is dealing with fuzzy data. So, I'm very much looking forward to hearing what she has to tell us. And Beatriz, the floor is yours.
Well, good afternoon. And first of all, thank you very much for the kind introduction. I don't see, yeah, like this. It's a pleasure for me to be part of this SIPTA Seminar series. And I should warn you, as Sebastian and Enrique have said, that my research does not cover imprecise probabilities, but I deal with imprecision in the nature of the data that we analyze. And I hope that you find some connections with your research interests and that we can discuss about that afterwards. So my research lies in the middle of two worlds because it combines the robust statistics techniques with the statistical analysis of imprecise valued data. So we have to start by motivating the use of this kind of data. And the reason is that we find imprecision in many real-life situations from fields as different as social sciences or medicine, engineering, and so on. And we could distinguish two kinds of situations where we find this imprecision. First of all, when we want to deal with a random variable or vector that is imprecisely observed, like it happens, for instance, when you want to determine the age of a sedimentary layer by using radiocarbon dating techniques. Or secondly, what you want to analyze an attribute that is essentially imprecise, like it happens, for instance, when you deal with human valuations. There are several ways to model this imprecision, and in this work, we're going to use fuzzy numbers, which are one-dimensional fuzzy sets. Well, this is the outline of the talk. First, we're going to explain the particularities of this data space. Then we're going to review some basic notions about robust statistics. And the third part is the main part, where we are going to adapt these notions from robust statistics to have robust central tendency measures for fuzzy value data. And as you see, there are several alternatives that we can choose that have been already introduced in the literature, and we're going to explain their main ideas, differences among them, and so on. In the fourth part, we're going to give some hints about how to simulate this data and the main conclusions that we have obtained in the empirical comparative studies. And we are going to finish with a few feature directions. Well, so in this slide, you can see a small sample consisting of 6 fuzzy numbers. Each fuzzy number is represented by a function. And in this case, you can see that they all have a trapezoidal shape. That is really common in practical applications because to ease the study, for instance, when we collect information about the responses to a survey, it is more comfortable for people to give a fuzzy number of trapezoidal shape or triangular shape than a general fuzzy number. But the definition that you see here is the general one. So we are going to denote by f sub CR the space of all fuzzy numbers, and each one is a function, a mapping that associates a real number with a value in the unit interval. We are going to see the interpretation just in a while. Such that all its alpha level sets that are represented by this formula are non-empty compact intervals of R. So what does an alpha level set represent? Once you fix the value for alpha, the alpha level consists of all the numbers such that their degree of compatibility with the attribute you represent is at least alpha, is large enough. Because the interpretation is that one, the degree of compatibility of each real number with the attribute represented by you, by the fuzzy number. For instance, here you can see a very typical example where the fuzzy number represents the attribute being a tall person. So if we refer to this person on the right, we could see that it's tall, and we're going to assign a high degree of compatibility, a value that is close to 1. But if we refer to the person on the left, then the degree of membership or compatibility decreases a lot. Well, and how to characterize these fuzzy numbers in order to work with them? Well, we're going to see several alternatives. The first one is the support function characterization. It is an extension of the support function for sets. And it uniquely describes the fuzzy number, but it is true that in practice, it may be difficult to handle. It is not as easy to specify as the other characterizations that we're going to see. For instance, one way, alternative way to represent the fuzzy number would be to refer to the extremes of all the alpha levels. For instance, here you see for this alpha level, we have the infimum and supremum, and we would repeat that for all the possible choices of alpha. And this is another way to uniquely describe the fuzzy number. And you may think, well, here you are using a characterization of an interval. What happens if I use a different characterization with, like for instance, that one that considers the center or the midpoint and the spread or the radius of the intervals? So we would have something like this. This is a representation, but it does not characterize a fuzzy number because we don't have necessary and sufficient conditions to assure that. Okay, so that is why we call it representation. If we want to extend the idea of characterizing the fuzzy numbers in terms of a center and the imprecision, we could deal with the mid LDEF RDEF characterization. So we have 3 terms here. The first one is the indicator of the center because we consider a midpoint, but not all the midpoints of all the alpha levels, just a fixed one. It's arbitrary, but we fix it. That is the beta that we select. And once we have fixed the center, we calculate the deviations to the left and to the right. Those are the indicators of the shape of the fuzzy number. And in this way, we can establish necessary and sufficient conditions to uniquely describe the fuzzy number. In case fuzzy numbers are symmetric, this coincides with the previous representation, but in general, it's something else. Well, and once we have the idea about the data, we need some operations in order to develop statistics. And the 2 most important operations from the statistical point of view are going to be the sum and the product by a scalar. They are defined by means of Sades extension principle, and that is the first formula that you can check in this slide and afterwards for the product by a scalar. But this is totally equivalent to the level-wise extension of the usual interval arithmetic. For instance, here for the sum, you see that for each alpha level, the alpha level of the sum coincides with the Minkowski sum of the corresponding intervals. We can see it in the graph where we have these alpha levels here. The Minkowski sum is this interval plotted in yellow, and if we repeat that for all alpha levels, we would get the fuzzy number u plus v, and the same for the product by this color. The most important remark regarding the arithmetic is that this space with these two operations is not linear. It is a convex cone, because if we sum this fuzzy number u with the fuzzy number -1 times u, we get a fuzzy number that is symmetric with respect to 0, but it is not the indicator function of 0, which is the neutral element for the sum. And this has very important consequences, because first of all, there is no difference operation that is always well defined and that keeps the connections that we have with the sum in the real settings. And in the second place, we cannot treat fuzzy numbers directly as if they were functional data, even when we have explained that they are functions. But the arithmetics are not the same. And you can see it in this example where we are adding two fuzzy numbers plotted in gray. And the functional sum is a function that is outside that unit interval, so it completely loses the meaning of a fuzzy number. So if we cannot work with difference operators, we're going to try to replace them by metrics, by distances between fuzzy numbers whenever this is possible. And there are different choices for the metrics that we can consider. Here you can see that we're going to talk about two L1 type metrics and an L2 type metric, but there are more choices that you could also work with. So about the L1 type metrics, we have the one-node distance by Diamond and Cluden, which is based on the infimum supremum characterization. And if you notice, the importance assigned to each of those deviations is the same. On the opposite, we have the second distance that is based on the second characterization that we saw that tried to extend the mid-spread representation. And in that one, we include a non-negative parameter theta that weighs the relative importance assigned to the deviation in imprecision, represented here by the L, the left and the right deviations, with respect to the deviation in center, in location, represented by the fixed mid. Those two metrics are topologically equivalent and yield separable metric spaces. And if you want to work with an L2 type metric, a suitable family of metrics is the d theta 1. The d theta 1 is based on the mid-spread representation, and it also includes the parameter theta with the same role that we have just explained. If theta is not larger than 1, this metric coincides with the well-known Bertoluzzi's metric. And if it is exactly 1, it coincides with the metric rho 1 by Diamond and Cluden. It also yields a separable metric space, and it is topologically equivalent to the previous ones. Or indeed, we could extend these metrics by considering an absolutely continuous probability measure phi in order to try to distinguish the influence of the different alpha levels in the computation of the distance. Anyway, when we choose the L2 type metric, the d theta metric, we can translate fuzzy numbers into functional data. We said that by definition, fuzzy numbers are functions, but we cannot treat them as functions directly. But if we identify each fuzzy number with its support function, and we're using this L2 type metric, then we have an isometrical embedding of the space of fuzzy numbers into the convex cone of the Hilbert space. If you use an L1 type metric, then the embedding is onto a convex cone of a Banach space, not a Hilbert space. That is why the choice of the metric is important here. And that means that we could adapt some developments from functional data analysis as long as we can guarantee that the outputs are going to be inside the cone. If we can't do so, or the adaptation becomes really complex, then we are going to use ad hoc techniques. Well, and to model the random mechanism of producing this kind of data, we're going to define random fuzzy numbers. They involve both randomness in the generation of the experimental data, but also imprecision. That refers here to the nature of the data that we have. Well, the mathematical definition is this one. For each alpha mapping, which is this function that we have here, we have to guarantee that that is a random compact interval. Or equivalently, we could say that a random fuzzy number is a Borel measurable mapping with respect to the Borel sigma field generated by the topology associated with this metric, or with any metric that is topologically equivalent. And here at the end of the slide, you can see other alternative definitions in terms of those characterizations that we mentioned before. For instance, anytime that you see infimum, supremum, left deviation or right deviation of the alpha mapping, then we have that those are real valued random variables. And what happens if we want to summarize the central tendency, the location of a random fuzzy number? Well, a natural attempt and the best known location measure is the Ullmann type mean, which is defined alpha level-wise by these intervals whose extremes are the expectations of the extremes of the alpha mapping. The corresponding estimator, the sample Ullmann type mean, is defined by this formula, and as you see, it is coherent with the arithmetic that we explained before. Well, indeed, here we need to refer to a simple random sample, which is just a collection of n independent random fuzzy numbers, or all of them identically distributed as the random fuzzy number x. And we do not need to explicitly define independent random fuzzy numbers because the independence, the notion is inherited from the Borel measurability of the random fuzzy number. So we can properly refer to these notions without stating them explicitly. Well, the Ullmann type mean fulfills very nice properties. For instance, as you see here, apart from being supported by strong laws of large numbers, it is additive and so on. I am interested in this last property because we're going to see it afterwards again. So the Ullmann type mean is the Fréchet expectation for the d theta metric. That means that it minimizes the expected square distances to the random fuzzy number. But it has an important drawback, and we're going to illustrate it by means of a very simple example. Imagine that we ask 4 people to express the perception about the taste of a certain kind of chocolate. What happens if 3 of those 4 people love chocolate, but 1 doesn't? That maybe we find a sample like this one. Here we have the outlier observation. And if we calculate the Ullmann type mean, it is this pink fuzzy number that does not represent what happens with the majority of the people that we have interviewed. It is too influenced by that outlier observation. Indeed, here you can see what happens if we just move one of the observations and how the Ullmann type mean is really influenced by that from the very beginning. The same happens if you work with scale measures, because the standard deviation is defined in terms of the Ullmann type mean. So it is also very sensitive to outliers or changes that are produced in the data. So it seems really convenient to try to adapt some notions from robust statistics in order to have measures that are more stable and are not so influenced by this outlying information. So about the notions of robust statistics, first of all, we're going to define the best known measures to quantify the robustness of an estimator. Well, the idea is that we try to summarize what happens with most of the data. We want to fit the behavior of the majority of the observations that we have. And an outlier is just an observation that deviates from that, from the behavior of the majority. So the measures of robustness that we're going to see are the final sample breakdown point, the influence function, and the max bias curve. The final sample breakdown point is a measure of how much contamination can an estimator tolerate until it breaks down. So formally, it is the minimum proportion of contaminated observations that makes the estimate be arbitrarily large. Here in the mathematical formula, you see that we have an original sample, the sample X, and Y represents the sample of the same size that is obtained by modifying, by contaminating K of those original observations from X. If we calculate in the classical settings the final sample breakdown point for the mean, we're going to get the minimum possible final sample breakdown point, which is 1 over n. And the median gets this number that is the maximum possible final sample breakdown point for translation equivalent estimators. That means for the estimators that fulfill this condition. When we do a translation of the data, then the estimator itself suffers the same translation, the same transformation. What happens if we want to adapt the final sample breakdown point to the fuzzy valued framework? That we need to replace the norm of this difference by the metric, any metric that we want to consider. Well, the second option, the influence function, focuses on local contamination instead of the global contamination that we have just seen. So for that reason, it contaminates the original distribution F by using here, as you see, a contamination proportion epsilon and the degenerate distribution at a point X. So the influence function determines how it is the estimator influenced by that small contamination at the point. It is very natural to think that we want bounded influence functions. So that contamination does not have a very large impact on our estimator. Well, in the case of fuzzy valued frameworks, we have not adapted the influence function yet. That is an open problem because, as you see, it depends on families of distributions, and we don't have realistic families of distributions for random fuzzy numbers yet. Okay, so this is still pending. And the third choice is the max bias curve. It is the study of what happens in the middle, because we have seen what happens when the contamination proportion is too much, so the estimator breaks down. That was the final sample breakdown point. And we have also mentioned what happens when we have an infinitesimal contamination proportion. But what happens when we have a contamination proportion that is a bit larger, but it is still tolerated by the estimator? Well, that is described by the max bias curve, which is defined as this. As you see, we see the supremum of all those deviations for the estimator when we consider the regular distribution and the contaminated distribution. And if we want to compare two estimators, the one with the smaller maximum asymptotic bias, the smaller max bias curve, is going to be more robust. And in this case, we have studied the max bias empirically for some kind of distributions that are frequent in our simulations. For the theoretical study, already in the classical settings, it presents a lot of complexity. It is difficult to calculate the max bias curve exactly, so it is really useful to find empirical approximations, and that is what we adapted for the fuzzy valued frame. These are the measures of robustness, but now we need some ideas of how to define measures for central tendency or for a scale, but in a robust way. So for location, we could replace the mean by the median, a tree mean, an estimator of location. And for the scale, even when we're not going to refer to the scale a lot due to the time that we have for the talk, but we are going to mention just one of these measures, we could skip the standard deviation and replace it by the interquartile range, the median absolute deviation, or an estimator. Well, so now we are going to adapt these notions to the fuzzy valued frame. We're going to combine them. The first choice, the first approach that we followed was to extend the notion of median. So the median for a real value random variable can be thought as the values that are in the center of that distribution. But we have a problem here because we don't have a universally accepted total order in the space of fuzzy numbers. And that means that we have to use a different approach. But for real value random variables, we can also define the median as the value that minimizes the expected distance to the random variable. And that is what we adapted in this definition. As you see, we use a general metric here between fuzzy numbers, and we use an analogous formula for the fuzzy valued case. If we want to refer to the estimators, and we have a simple random sample from this random fuzzy number X, we must choose a particular metric here. And you are going to see that the choices that appear more frequently in the literature are those L1 type metrics that we explained before. So we have the sample one norm median in this slide, and in the next slide, we're going to see the sample median corresponding to the other L1 type metric based on the mid, LDEF, RDEF characterization. Well, so it can be proved that with this particular choice of D being the one norm distance, the sample one norm median is the fuzzy number valued statistic such that its alpha levels are given by these intervals whose extremes are the medians of the extremes of the alpha mappings. Here we have medians of real valued random variables. And in case they are not unique, we need a convention in order to guarantee that this is a fuzzy number. So we're going to select the usual convention. We choose the midpoint of the interval of possible medians. For the second choice of the metric, something similar. Here we have the alpha level written in terms of that characterization. And in both cases, you see that they fulfill very good properties. We have a fine equivariance, we have robustness because they achieve the maximum final sample breakdown point, and a strong consistency to the population median. Well, it could be possible to choose an L2 type metric like the d theta metric. But it is true that the minimization problem gets much more complicated. So for instance, in the literature, you are going to find that option just in the interval valued case, but the adaptation to the fuzzy value setting is still pending. Well, apart from these nice properties, if we compare them with the medians of real value random variables, we can notice that there are some differences because, for instance, they do not need to coincide with one sample observation. That is what we see here in this very simple example where we have 3 fuzzy numbers. And they do not keep the shape because in this example, the 3 fuzzy numbers have a trapezoidal shape. And you see that the sample medians that we have do not preserve that shape. That is why we're going to introduce fuzzy medoids. Fuzzy medoids just add a constraint to the minimization problem so we can guarantee that the shape is preserved and that they are going to coincide with one sample observation. The constraint is that we are going to search for this minimum just inside the sample of fuzzy valued observations. And the theoretical properties are more or less the same. You see that we have still the affine equivariance, the robustness, a strong consistency to the corresponding fuzzy median. And we have guaranteed that the shape is preserved and the existence is always guaranteed. Okay, the uniqueness may not be guaranteed, as you see in this example. For computations, we have checked that they provide very competitive results with the comparison of fuzzy medians. It is true that when you increase the size of the sample, then they become quite complex computationally. But you have to take in mind that afterwards, after you get this central tendency measure, you are going to apply it for some statistical procedures, and you are going to calculate, for instance, distances with respect to the center. And once you have a medoid, as they keep, for instance, the trapezoidal shape, all those distances that we explained before have a particular expression, an explicit expression for them. So it may compensate the fact that the fuzzy medoid takes a bit more time to be calculated than the fuzzy median in those cases. Well, just to have a real life example, some data, and to compare these two measures, we are going to talk about a survey that we did in 2014 at a school here in Oviedo in Spain, Colegio San Ignacio. We adapted the well-known questionnaire based on the TIMSS PILS joint study, which assessed fourth grade students in mathematics, science, and reading. So they were children of 9-10-year-old. For the original questionnaire, they had to use a 4-point Likert scale. So they had to choose among these options: disagree a little, disagree a lot, disagree a little, and agree a lot. And we also required a second answer in terms of a fuzzy rating scale. That means that the children had to give a fuzzy number, well, trapezoidal fuzzy number, that represented their opinion about the item. And we conducted the survey on 69 fourth grade students. So on the left, you can see how they had to answer those questions. For the fuzzy rating scale, we considered the usual referential from 0 to 10, and here they could see the equivalence between those two ways, two scales for answering the item. And on the right, the sample that we collected. So if we focus on the item, my teacher of mathematics is easy to understand, and by the responses given by male students, we have this sample. And in these plots, you can see how we get the sample Ullmann type mean, the fuzzy medians here on top, and the fuzzy medoids, the corresponding fuzzy medoids. There are two measures for each of these kind of measurement, because we have compared in solid line the estimate for all the sample, and in dashed line you have the estimate when we remove the most outlying observation, that response that appears on the left of the graph. For the Ullmann mean, you get the clearest difference between those two estimates. For the fuzzy medians, you can see that the deviation is much smaller, and for the fuzzy medoids, in this case, there is no deviation because they coincided in both cases. So now we're going to refer to a completely different approach, which is that of trim means. The idea for trim means is really simple. You just remove those observations that lie in the tails of the distribution, and you calculate the mean of the remaining observations. But when you talk about trim means in a more complex space, then that is not so easy, and you have to adapt it. So here, as you see, we have the trimming region, which is the subset of the non-trim observations. We have to decide the size of the trimming region in advance. as you see, depends on this parameter beta, and beta is what we call the trimming proportion. So once we set beta, the trimming region just represents the subset of that size that has the minimum sample variance, where the observations are more concentrated. We remove the rest of the observations and we calculate the unman-type mean of the non-trim observations. That is the empirical fuzzy trim mean. Well, this is not the only way to calculate trim means, because you can adapt it, for instance, in terms of depth measures. We're not going to see the formula here, but we're going to see just the intuitive idea. So in the bivariate case, not to complicate this, imagine that we have this sample and the trimming region is represented by the red points. There you can see that the degree of belonging to the trimming region is 1, and the observations that are trimmed at those green observations. So here we have a completely inflexible, strict difference between the trimming region and the rest. If you deal with a statistical depth function, like for instance the two-key depth or the half-space depth, then you are going to see that the degree of centrality of those observations can be in some way quantified. Okay, so the depth just quantifies how central an observation is. And the trim mean would be the calculation of the mean of those observations with the highest depths. Well, empirical fuzzy trim means present nice properties like the ones that we saw for the previous measures, but regarding the robustness, it is very important to refer to the trimming proportion because they achieve the maximum final sample breakdown point if that trimming proportion equals 0.5, but otherwise the robustness is not as much. There are strongly consistent estimators of the population version of the fuzzy trim mean, and they have to be approximated by an algorithm. Well, what happens if we don't want to remove the observations directly? Because this approach of trim means may not be so comfortable in practice. For instance, if those observations represents experts' valuations, it may not be very easy to discard just of those valuations. So an alternative is to use fuzzy M estimators, because fuzzy M estimators assign a weight to those observations, and if that weight is really small because that observation is clearly outlying, then it's not going to have any influence on the final estimate. So we need a loss function to assign those weights. A loss function, a rho, has to fulfill these two assumptions that we have here. They have a continuous derivative, they vanish at 0, and it is a non-decreasing function. And once we have that, if you check the definition for the fuzzy M estimator of location, you can notice that it is very similar to the minimization problem that we presented for fuzzy medians, but we have included this loss function rho to weigh the importance of those distances that we are considering. Well, so some particular choices that are well known are the Hoover loss function that depends on this tuning parameter, and as you see here in the plot, it is a convex function close to origin, but afterwards it is linear. This is to try not to have a lot of impact when outliers appear, because for rho, you could also choose the square function, and that produces the Ullmann type mean, because we saw that it was the Fauché expectation. So that means that the robustness of M estimators clearly depends on the choice of this loss function. So in this way, we have more robust outputs. Another choice would be the Humboldt loss function. And in this case, we have 3 tuning parameters. The main difference, as you see here, is that it is bounded. For large outlying observations, the weight in terms of the loss function is always the same. Well, and about the properties, they are more or less the same. Here we need some mild conditions, for instance, for the strong consistency, for the robustness with the humble loss function, whereas with the choice of the Hoover loss function, it always achieves the maximum finite breakdown point, for the existence itself, and so on. But it is guaranteed that under those additional conditions that we refer to as the representer theorem, we can calculate fuzzy M estimators, and it is guaranteed that they belong to the space of fuzzy numbers, because we can express them as a weighted mean of the sample observations. Well, the thing is that there is a clear drawback, which is the lack of affine equivariance. In fact, they are translation equivariant, but not scale equivariant. And that is an important drawback in practice, where the change in a scale may invalidate the results that we have. Well, they also need an algorithmic calculation and so on. Well, so to try to avoid the problem with the lack of scale equivariance, it is very important to choose the tuning parameters in an appropriate way. So first of all, what we do in practice is to take a robust seed of the center, like for instance, the calculation of a fuzzy median. Once we have that, we evaluate all the distances between each observation and the seed, and then we consider as parameters the median, the 75th percentile, and the 85th percentile of those distances. And with this, we cope with that problem, and the empirical results are very nice. Well, but apart from this, M estimators present a drawback when you also want to work with the scale measure. We're not talking about the scale here, but if you are using fuzzy medians, there is a natural measure which is called the median distance deviation about the median, which has been used in the literature. For fuzzy tree means, we can refer to the standard deviation of the tree mean region, so it's also natural. But for fuzzy M estimators, we don't have that. There is no scale estimator that is naturally available for them. So in the classical settings, they introduced a new measure that is called S-estimator. The S-estimator preserves more or less the good behavior of M estimators, but they have an associated measure of scale. We also need the loss function as for M estimators, and you see that the assumptions are very similar. The only difference is that here we only consider loss functions that are bounded. And the definition is this one that you have here. It provides you with both an estimator of location and an estimator of a scale, but the aim is to minimize the scale. You minimize the sigma subject to this constraint. In this constraint, you have that the mean of the loss function evaluated on the standard distances equals a fixed value. And this is a value that you can choose between 0 and the upper bound for the loss function. About the theoretical properties, well, we are currently studying fuzzy estimators, but we have already proved that they are well defined because they are Borel measurable mappings under mild conditions, that they extend real valued estimators, that the existence is also guaranteed by using an analogous representer theorem, and that they are affine equivariant. But we still have to check, for instance, the robustness from a theoretical point of view. We have just considered some empirical comparisons by this moment. And for those empirical studies, for the simulations, we have adapted the FAST algorithm from the classical framework that was presented in this work by Salivian, Barrera, and Yohai. Well, for fuzzy estimators, the best known loss function is the 2-key p-square loss that you have here. And it is quite interesting because it depends on just one tuning parameter as the Hoover loss function, but you can see that the shape is more similar to that one that we saw for the Humber loss function. Well, and how do we work with this from the practical point of view when we want to simulate and to carry out some empirical studies? Well, we're going to see how to simulate these trapezoidal fuzzy numbers. So in this kind of works, we searched for the estimator that provides the nearest fuzzy estimates to the corresponding population value, but the nearest can be understood in terms of the mean square error, like here, or in terms of the bias, in terms of the variance, and so on. The sample size is denoted by small n, while capital N represents the number of Monte Carlo repetitions in order to approximate the population measures. We have considered trapezoidal fuzzy numbers because, as I said before, that is the most common case in real-life applications. And for distances, when we use the d theta metric, we usually work with theta equal to 1/3 because that guarantees that the distances between all the points that we have in the corresponding alpha levels are equally weighted. And we have used different probability distributions and different scenarios regarding contamination because we want to establish that they are robust. So in that way, we introduce two kind of parameters. CP represents the contamination proportion, and here you have the range that we have considered, and CD, the contamination magnitude. That is the separation between the contaminated and the non-contaminated subsamples. So to generate trapezoidal fuzzy numbers, we use 4 real-valued random variables, which are x1, the midpoint of the one level, and then 3 random variables that represent imprecision, deviations. We have x2 as the spread of the one level, x3 is the difference between the infima of the one level and the 0 level, and x4 the difference between the suprema of the 0 level and the 1 level. And just to illustrate this, 2 possible cases that we have considered in the literature are these ones, where in the first case you have independence among these 4 real-value random variables, and in case 2 we introduce some dependence because you see that x2, x3, and x4 depend on the random variable x1. But you could also consider different distributions, like for instance, a non-symmetric distribution for x1 and so on. Once we have this, we have to approximate the population location measures, and for that, we usually use Monte Carlo repetitions. Once we have that, we generate again n samples for each of those situations, and we contaminate, we introduce that contamination fraction that we referred to as before, a CP. So for the contamination, you need a different distribution. You see that in case 1, for instance, we changed the parameters of the normal distribution for x1 and also the degrees of freedom of the chi-square distribution for the rest, and we translated those variables. And in case 2, something similar. So once you have the contaminated samples for each of those cases and scenarios, you can calculate the mean square error, or the bias or variance, as I said before. The formulas are analogous to those formulas that we have in the classical settings, but we have to adapt them in order to use metrics instead of differences again. And for the main conclusions about the empirical studies that we have carried out, we have seen that there is no best estimator in all cases. The choice of the best estimator is not uniform through all these situations, but that is something that is not worrying because it also happens in the classical settings. The outputs also depend on the distributions that we choose for simulating the data. But in general, we could say that the fuzzy M estimators have presented a good performance for low or moderate contamination levels, and when the contamination level is close to 0.5, then the best option was to use fuzzy trim means with that trimming proportion. And about fuzzy estimators of location and scale that have been more recently introduced, we have not compared them with all these measures yet. We have just compared them with fuzzy trim means and the associated scale measure, and they have very promising empirical results. They have the most stable performance. It is really clear. So as future directions, we would like to complete this theoretical study of fuzzy estimators and also to develop robust statistical techniques based on all these measures, because now that we have robust measures for central tendency and for the scale, we could use them for instance, adapting the K-Medoids algorithm for clustering, or the estimator could be used for having a robust regression between fuzzy value data and so on. Well, here you can see some basic references about all these notions, but of course, the list could be much more exhaustive, and the acknowledgement about the funding. That is all. Thank you very much for your attention.